Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to do Unit 6, Lesson 7, Exponential Models Based on Percent Growth. Before we begin, let me remind you that you can find the worksheet and a homework assignment that go with this video by clicking on the video's description. As well, don't forget about the QR codes at the top of every worksheet. Use your smartphone or your tablet to scan that code and be brought right to the video that ties into the worksheet. Okay, let's begin. In the last lesson, we saw how to quickly increase or decrease a base amount by a certain percent. Today, what we're going to do is build percent, or we're going to build exponential models based on that idea. So let's jump right into it. A population of fruit flies is growing at a constant rate of 6% per hour. That probably seems pretty fast. But fruit fly populations grow pretty fast. The population starts out at t=0 with 28 flies. Using what we learned in the last lesson, determine the population after each of the following amounts of time. Show the calculation you use as repeated multiplication. All right, so let's take a look. Well, we're increasing at 6% per hour. So after 1 hour, we're going to start with that 28. We're then going to multiply by 1 plus 0.06. So we're going to do 28 times 1.06, and we're going to get 28, whoops, sorry, not 28. Let's try that again. I can't do that multiplication in my head. 29.68. So we'd probably say that that was 30. Now we're going to continue to use that 29.68 though. After 2 hours, we've got 29.68 times 1.06 again. But really, that's 28 after it's been multiplied by 1.06 twice. Think about that, right? We multiplied once to get to 29.68, and then we multiplied again after 2 hours. That's going to be 31.46, or about 31 fruit flies. Now, after 3 hours, we're going to take that 31.46 and multiply it by 1.06. But again, that's going to give us the same as taking the 28 and multiplying by 1.06 to the third. If this feels familiar, it is. We did this back when we were first looking at exponential growth and decay. All right, and that's about, let's say, 33. Okay? So all we're doing every time period, every time period of increase of 1 hour is we get to multiply by 1.06 again. Because we keep multiplying by the same quantity again and again and again, we can represent that repeated multiplication in terms of an exponent. Now watch how easy it's going to be to create a formula. Right? We want a formula for p as a function of the number of hours t. Well, it's this easy. P of t, we start with 28. That's our original amount. We multiply it by 1.06, and we raise it to the t because this represents how many hours have gone by. And that's it. Right? And that's exactly what we did. Look, in each one of these cases, let me go in red instead, right? After 1 hour, we did 28 times 1.06 to the first. After 2 hours, 28 times 1.06 to the second. After 3 hours, 28 times 1.06 to the third. It's simple, right? Let me go back to blue. What's the value of p of 24? Well, that's simple. I mean, that's just using this formula. P of 24 is going to be 28 times 1.06 to the 24th. Enter that into your calculator very carefully, and that's going to give me an obnoxious decimal, 1.13370, etc. But we're talking about fruit flies here. So 113, right? It doesn't make sense to say that there are 113.37 fruit flies. We're going to say there's 113. Now, letter D, very, very important. What does the calculation you made in C represent about the fly population? Then it asks us to state the range of the population function over the domain interval 0 to 24. All right, simple enough. So that P of 24 represents the fact that there are 113 flies at the end of one day, right? Now, why do I say one day? Well, remember, T represented the number of hours, right? So P of 24 is 24 hours. Now, what's the range? The range, right, are the outputs. Now, what did we start with? Well, we started with 28, and we ended with 113. So there's our range. All right? Or we could use interval notation, 28 to 113. Now, it's a little bit incorrect, both of these, by the way. I just want to point that out. It's a little bit incorrect because we can't have a fraction. We can't really have a fraction of a fruit fly, right? So actually, the range would be best stated as 28, 29, 30, all the way up to 113. All right, this is actually the best way of writing the range. These are a bit incorrect because they would imply that, let's say 32.7 fruit flies existed. But sometimes we'll still use this notation with the understanding, let's say, that the values can only be integers. All right? Now we're going to continue on with this problem, but I gotta flip the page, so that means I have to clear the text. Pause the video now, write down what you need to. All right, here we go. So, there's our model. P of t equals 28 times 1.06 to the t in nice huge font. Letter E, using your calculator, sketch the graph of this function over the interval 0 to 24, and p is greater than 0, less than 120. All right, now we've done a bit of this already on our graphing calculator. Okay, so I do want to open up the TI-84 Plus right now to see what it looks like. All right, there's my calculator. So let's do it. As always, in order to graph something on our TI-84 Plus, we're going to go into the y equals option. All right, we're going to clear out any equations that might be there. Let me pause to give you a chance to clear them, and give me a chance to clear them if they're there. Okay, now let's enter this. Now I know the formula is in terms of t, but we're going to put it in terms of x. So we've got that 28 parentheses 1.06 parentheses. Make sure to use that caret button, that raise to the button, raise to the x. Huge mistake if you just have 1.06 times x. We want 1.06 raised to the x. Okay, we've got the formula in there, so we want to just look at it, right? We want to look at it, make sure it's right. Good. Now we want to noodle around a little bit with the window. Noodle around, very technical language. So go into the window. Okay. Now the problem says 0 to 24 for t, but that's now my x, so my x min is going to be 0. My x max is going to be 24. Go down a little ways. My y min is going to be 0. And my y max is going to be 120. All right. Make sure that looks right. Check your Windows settings. Take your time. No rush. All right. Now let's hit graph, okay? And again, we see that classic exponential increasing exponential. And of course, it's increasing because the base is 1.06, right? And 1.06 is greater than 1. All right. It says mark the y-intercept. Our y-intercept was 28. We could even mark this point out here. It doesn't say that we have to, but we could. And what was that? That was 24 comma 113. Right? And again, in a certain sense, this graph is a little bit incorrect because it's implying that we're getting all these fractional numbers of fruit flies. It should just be a bunch of dots going along here, or maybe not even dots, maybe even a step function, but that's awfully complicated. So we're going to keep it the way it looks, all right, with the understanding that we can't have a fraction of a fruit fly. All right, let's get rid of the TI-84 plus now. Bye-bye, calculator. And let's clear out the text. So pause the video now if you need to in order to copy down that graph. Hopefully you've got it sitting on your own calculator. All right, here I'm going to clear it out. All right, so let's take a look at a nice multiple choice problem. Okay, now what we want to be able to do is look at this and interpret it. It says if the savings in a bank account can be modeled by the function s of t equals 250 times 1.045 to the t, which of the following is true? So pause the video now and think about this a bit, okay? All right, let's take a look. So we want to interpret this. Now, all exponential functions kind of look like this, where a is the starting amount. So that is clearly 250. All right, so that means that it either has to be choice 1 or choice 3, one of those two. These guys are out. That's out, and that's out. We are not starting with $2.50. Now, on the other hand, right, we've got the 250 times 1.045. But remember, the way that we look at this is that's 250 times 1 plus 0.045. This is a little bit tricky, but this is 4.5 divided by 100, right? So that indicates that it's going up by 4.5%. So the correct one is choice 3. If it were going up by 45%, two things. Number one, if it were going up by 45%, the multiplier would be 1.45. And number two, put all of your money into that investment option. Almost nothing goes up at 45%. Actually, very little increases at 4.5%. Boy, that would be great. Anyhow, I'm going to clear out the text, and then we're going to take a little bit at creating some models where it's decreasing. All right, here we go. Let's keep going. All right, as water drains out of a pool, the depth of the water decreases now. Decreases, very, very important. The depth of the water decreases at a constant percent rate of 20% per hour. Okay. The depth of the water when the draining begins is 12 feet. Okay. As in number 1, find the depth of the water in the pool after each of the following times. Okay, so this really builds off what we did last lesson. So we start with 12 feet, but we want to decrease by 20%, right? So we're multiplying by 1 minus 0.20, or 12 times 0.80. Now again, think about that for a minute, right? That really means that when we decrease by 20%, 80% remains. It's always about what remains. 80% remains, right? And of course, multiplying this out is pretty easy, 9.6 feet of depth. After 2 hours, we're going to take that 9.6 and multiply it by 0.80, or by 0.8, whichever. I like the 0.80 because it really hammers home the 80%, the 80%. But again, that's actually our 12 times 0.80 twice, right? We've really multiplied the 12 twice by 0.80, which then gives us 7.68 feet. Notice I don't really feel the need to round that to the nearest foot. There's absolutely no reason, unlike population, where those depths have to be nice whole numbers. In fact, they typically won't be. Finally, after 3 hours, we'd have that 7.68 times 0.80. But again, that's just the same as multiplying 12 by 0.80. to the third. So after 3 hours, our depth is down to 6.144 feet. Okay. Now letter B. Based on letter A, create an equation that gives the depth, d, of the water in the pool as a function of the time in hours it has been draining. I bet this is really simple for you now, right? So d of t. Okay. We start with 12 feet. Our multiplier is 0.80 or 0.8, doesn't matter, raised to the t. Again, just look at how much sense this makes. Right, there it is, to the first, to the second, to the third. Every hour that goes by, we get to multiply by 0.8 again. It's great. All right, so I'm going to clear this out. Pause the video now. Okay, here goes the text. All right, so there's my function. D of t equals 12 times 0.80 to the t. All right, we're going to use our calculators again. Using your calculator, sketch the graph of your function over that interval. Mark the y-intercept with its value. Let's bring it open again. I always got to snap my fingers. There's my TI-84 plus. Excellent. All right, sorry about the crowded nature again, but let's go into y equals. All right, probably going to have to clear out that last equation and any other ones, so let's clear them out. Okay, let's enter that. So in y1, I'm going to put in 12, parentheses, 0.80, or just 0.8, parentheses, raised to the x again. I know, it'd be nice to do t, but we're doing x. Raised to the x. Step back, look at the function. Make sure you've got that raised to in there, that little caret. Okay. Let's go in and adjust the window. All right, so hit your window button. All right, again, it's all laid out here. My input variable goes from 0 to 20, so x min is 0. Change it if it's not already 0. My x max, though, is 20. All right. My y min, which is actually my depth, is 0. And my y max is 15. Okay. So again, let's check over the window. Take a look at it. Make sure everything's good, nothing strange. Often when you have graphing errors, it's because things have happened, like you've put a larger value in for y min than y max. The calculator gets very confused by things like that. Remember, it's not a very smart machine. It's going to do exactly what you tell it to do. So it all looks good. Let's hit the graph button. I love the graphs of exponential functions. They're pretty cool. There it is. All right. Let's sketch it. All right, we'll start it right about here. And it's my hockey stick again, looking like that. These things are getting a little bit better. Maybe put an ending point there. It says mark the y-intercept with its value. So the y-intercept was 12, and then it just decreased. And again, of course it decreased because the base, b, was less than 1. Right? It's all about the base being greater than 1, like in the last problem, that was 1.06, or the base being less than 1 in this problem, 0.8. Now letter D. It's safe to cover the pool, right? To put a tarp over the pool after it reaches a depth of 1 foot or less. What is the minimum number of whole hours that we should wait to cover the pool? Explain how you found your answer. So go for it. Play around with this problem and see what you can do to figure out the answer to this problem to the nearest whole hour. All right, let's go through it. There's lots of different ways to do it, but given the fact that we just graphed the thing, given the fact that we know how to generate tables, that might be the easiest way to do this. So why don't we take a look at our calculator again, scoot it over to the other side. All right, now it's covering up my graph, which isn't the most helpful thing on earth, but at least we still have the calculator. And let's take a look at a table. Now, just to be safe, let's go into our table setup. You know, your tables might not be set up correctly, so go right up into your table setup. It's right up in here. All right. Remember, we have to tell the table where to start. We might as well start it at 0. So if your table start isn't at 0, do that. And then let's make the table go by ones. So that's my delta table, that little thing with the triangle there. Okay. And we can now see hour by hour what the depth is going to be. So why don't you go ahead and pop into your table. Remember, you get that by hitting the second and graph. Okay. So let's go into the table. All right. Well, let's write out the table. Let's provide some evidence. Now, I know it says x and y1, but remember, the x was really time in hours, and the y1 was depth in feet. And let's scan down the table. Remember, what we're looking for is a depth of 1 foot or less. So what I see, let's start right here, is at 10 hours, I see a depth of 1.2885. I see at 11 hours a depth of 1.0308, and I see at a depth of 12 hours 0.82463. So we're very, very close at 11 hours, but not quite, right? We're still above the 1 foot limit at that point. In fact, the first time, we'll switch back to blue here, that the depth is below 1 foot of water is 12 hours. So we're going to wait a full 12 hours before we tarp this pool. Okay, we'd probably be safe after 11 hours, but to be very safe, we should wait 12. All right. So I'm going to clear out the text. First, I'm going to get rid of the TI-84 plus though. Bye-bye calculator. Pause the video now if you need to look at the all the work that we've shown. All right, I'm going to clear out the text. All right, all gone. Let's move on to another problem. Exercise 4. Which of the following equations would model an exponential quantity that begins at a level of 16 and decreases, gosh, is that an important word, at a rate of 8% per hour? So see how much you understand this with a very, hopefully, easy fluency problem. Pause the video now and think about your choices. All right, let's go through them. So y equals a times b to the x. A is always what you start with, 16. In this case, b will be 1 minus 0.08 raised to the t. That's going to be 16 times 0.92 raised to the t. That's going to be choice 1. Remember, if we're going down by 8% per hour, that means we have 92% remaining. Okay? So that's a good check for you. Did you get that question right? All right. I'm going to clear out the screen. All right. Let's try another somewhat easy fluency question. Exercise number 5. If $350 is placed in a savings account that earns 3.5% interest applied once a year, then how much would the savings account be worth after 10 years? Pause the video and see if you can figure this out. All right, let's go through it. Well, hopefully you understand that when you earn interest, that means you're increasing by 3.5%. So what we've got is we're starting off with 350. Then we get to multiply by 1 plus 0.035. But the key is we get to do that 10 times. 10 times, right? So we get 350 times 1.035 to the 10th. Carefully put that into our calculator. We get $493, 0.709, etc. So 493.71. All right. So a couple multiple choice problems to finish off the lesson just to see where you're at. All right, I'm going to clear this out. Okay, let's finish up the lesson. So today we used what we learned directly in the last lesson about percent increase and percent decrease to create exponential functions that model real-world phenomena. I really hope you appreciate how much more you can do at the end of this lesson than what you could do at the beginning. Now when you know that a certain thing is growing at a certain rate, you can predict it. No longer will you hear something like, yeah, the population of the United States is growing at 2% per year, and have no idea really what that means. That just means every year I multiply by 1.02, and it gets larger and larger. All right? For now, though, I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking,